Hey everybody, we're starting Chapter 9. And Chapter 9 is on chemical equation calculations, which is also known as stoichiometry. Again, we're still in math land. So if Chapter 8 was a struggle, Chapter 9 is going to be a struggle too. Make sure that you remember balancing equations from Chapter 7, because we'll be using balanced equations to do stoichiometry. And you'll also need to remember the concept of the mole, and we're going to be doing more calculations that involve unit changes. So if that is still kind of a big black box of mystery, you need to unsolve it, okay? Let's go. Let's say that we have an equation like we do here. We've got nitrogen monoxide and oxygen gas combining to make nitrogen dioxide. Let's make a little table. We're going to talk about how much of each reactant we need and how much product we'll make. From the chemical reaction, we can look at the coefficients, which are the numbers in front. There's a 2, the implied 1, and the 2. This means we could take 2 molecules of NO2, 1 molecule of oxygen, combine them with UV, and we would make 2 molecules of nitrogen dioxide. Well, what if we had 200 molecules? Then we would need 100 molecules of oxygen. Combine them, and you would get 200 molecules of nitrogen dioxide. Let's say you had 2,000 molecules. Then you would need 1,000 molecules of oxygen, and you would end up making 2,000 molecules of nitrogen dioxide. We can also talk about this in terms of moles. We can use the coefficients. Let's say that we have 2 moles of nitrogen monoxide and 1 mole of oxygen gas. We would make 2 moles of nitrogen dioxide. So those coefficients are useful for interpreting a chemical equation. We can talk about it in terms of molecules or atoms, and the number of moles of each reactant we need and how much product we'll make. So that's what this slide says in words, that the coefficients of a balanced, keyword balanced, chemical equation represents the moles of each species involved. If we're dealing with all gases like we are with our reaction, you can talk about it in terms of moles, or you can talk about it in terms of the volume of gas, but only if they're at the same temperature. So that 2 could be 2 liters, 1 liter of oxygen, and 2 liters of nitrogen dioxide. But this is only for gases. And they have to all be at the same temperature and pressure. What this demonstrates is the law of conservation of mass, which we kind of already talked about in 2 ways. One, we introduced it in Chapter 3. And then when we were balancing equations, we said that the same number of atoms of each reactant needs to show up on the product side. That's conserving mass. If you have the same number of each element type on each side of the reaction, that means the mass on each side is going to be the same. So if you add together the number of grams that 2 moles of nitrogen monoxide and 1 mole of oxygen gas are together, you get 92.02 grams. 2 moles of nitrogen dioxide will give you the same thing. So mass is neither created nor destroyed during a chemical reaction. You can use these balanced equations to write mole ratios, and these can be used like unit factors. I'll show you what I mean. We're still using an equation with all gases, so keep in mind that for these mole ratios we can talk about moles, but we can also talk about volume. We'll start with moles though. We've got nitrogen gas and oxygen gas coming together with heat to make nitrogen monoxide gas. Remember, we said that these coefficients can be used to talk about moles. If I have 1 mole of nitrogen gas, then I need 1 mole of oxygen gas to complete the reaction. I just got those exactly from the chemical equation. What if I wanted to relate nitrogen gas and the product, nitrogen monoxide? Then I could say 1 mole of nitrogen gas for every 2 moles of nitrogen monoxide. Again, these numbers are just coming from the chemical equation. Let's write some for oxygen. If I have 1 mole of oxygen, I need 1 mole of nitrogen gas to complete the reaction. If I have 1 mole of oxygen gas, I will make 2 moles of nitrogen monoxide. So we're just taking the number of moles of each reactant and product and making fractions. Let's practice and use it to do some math, because those mole ratios can be used to calculate how much of a reactant you need or how much product you'll make. Our question asks, how many moles of oxygen react with 2.25 moles of nitrogen? We're going to do the same thing that we've been doing in Chapter 8, where we're writing out the question and we're figuring out what units we have and what units we need to get to. In this case, we have 2.25 moles of nitrogen gas, and our question is asking us how many moles of oxygen gas. For this, we need to use a mole ratio between the nitrogen gas and the oxygen gas, and we can write 2 of them. There's 1 mole of nitrogen gas over 1 mole of oxygen gas, and just like with all the other unit factors that we have, we can flip that over. 1 mole of oxygen gas over 1 mole of nitrogen gas. We're starting with moles of nitrogen gas, and we want to get to moles of oxygen gas. That means we need to cancel out the moles of nitrogen gas in the top, so we need that in the bottom. That's going to be the second one. We'll have the moles of oxygen on top, moles of nitrogen gas on the bottom. The moles of nitrogen gas will cancel, and we're just left with moles of oxygen, which is good because that's what we want. You do the math, and your answer is 2.25 moles of oxygen gas. So I said the S word earlier, stoichiometry. That's the use of relationships in a balanced chemical equation, again, balanced, to carry out calculations involving reactants and products. So that's what we're going to be doing. That's actually what we just did. We took the number of moles of nitrogen gas and figured out how much oxygen gas we would need to fully react with it. There are three types of stoichiometry problems that we're going to cover here. The first is converting mass of a reactant or product to another mass of reactant or product. The second is mass to volume, where we're starting with a mass and we need to figure out a volume of a gas. And the third, which is the easiest type, is volume to volume, where you have two gases and you need to figure out how much of one will yield how much of another. So this is a wordy slide, okay? I'm going to break it down for you when we do a problem, but I'll tell you the generic steps involved in solving a mass-to-mass stoichiometry problem. The first thing that you have to do is identify it. So in the problem itself, you will be given a mass of a reactant or product, and the question will ask about the mass of a reactant or product. So you have X number of grams of sodium chloride, and what is the mass of whatever product. That's a mass-to-mass question. The first step is to take the given mass, and let's put some realness on it. So A, B, and C are obviously not elements, but hopefully this will help you in terms of understanding the steps. So if we have this reaction, A plus B yields C, and we know that we have, let's say, 5 grams of A, and we want to know how many grams of C we'll make. The first step is to take the grams of A and convert that to moles. So you need to use the molar mass there. The second step is to use a mole-mole ratio to figure out how many moles of A will give you how many moles of C. So that one is always going to change. The third part is to convert the moles of C to grams of C, and we're using another molar mass here. That's the steps for mass to mass. Now I'll show you an actual problem. And this will help you. I'll do it kind of color-coded, and I'll use that same color coding throughout the lecture, hopefully, because, sometimes I forget what color I used. But I'm going to use the same colors to match up each step and show you, okay, if we stopped here, what unit would we have? If we stopped here, what unit would we have? So hopefully that will make it a little bit more clear. What is the mass of mercury produced from the decomposition of 1.25 grams of orange mercury 2 oxide? And in this question, we actually have the molar mass of orange mercury 2 chloride, or oxide, excuse me. So you don't have to figure that one out. The first thing you have to do is identify the problem. You're not going to have this lovely little title that says mass to mass problems. You're going to have to figure that out. What is the mass? Okay, so our question is about a mass of mercury produced from the decomposition of 1.25 grams of mercury 2 oxide. So we have to identify these two things. We have 1.25 grams, which is a mass. And the question is asking, what is the mass? So that is a mass-to-mass problem. Always identify that first, because that will let you know which unit factors you need to use to get from point A to point B. Now that we know that, we know we're going to need molar masses for each of these. The molar mass for mercury 2 oxide has already been given. That will not always be the case. The molar mass of mercury, you simply have to look at the periodic table. When you do that, you'll see something in the ballpark. Oops. I just rewrote the one for mercury oxide. That's not right. You'll see something around 200.59. My periodic table has 3 decimal places after the decimal point. Yours may only have 2. That's okay. Now that we've got our molar masses, we can start setting up the problem. So here's the plan. We're starting with grams of mercury 2 oxide. The first step is to go from grams to moles. And we're going to use the molar mass of mercury 2 oxide to do that. That's something that we did in chapter 8. Then we're going to take those moles of mercury 2 oxide and convert them to moles of mercury. This is using a mole ratio. So we need to make a mole ratio from the chemical equation that tells us how many moles of mercury for how many moles of mercury oxide, mercury 2 oxide. The final piece is taking the moles of mercury and converting to grams of mercury using the molar mass. Now let's write all of this out. This is our given information. That's what we're starting with. The 1.25 grams of mercury 2 oxide. Our first unit factor is going to involve the molar mass of mercury 2 oxide. If we're looking to go from grams to moles, that means we need to have the moles in the top and the grams in the bottom. Make sure that when you're writing out your unit factors, you label everything. Because you've got 2 molar masses, you need to make sure that you're using the right one. Next comes our mole ratio. Let's write our mole ratios up here next to the chemical equation, and then we'll choose which one we want. So we need to relate the mercury 2 oxide and the mercury. So let's write a fraction with the moles for each. We've got 2 moles of mercury 2 oxide and 2 moles of mercury. We can also flip that around. Put the mercury on top and the mercury 2 oxide on the bottom. Which one is going to actually help us? Because we're trying to get rid of moles of mercury 2 oxide. If we want to do that, then we want to use the second one here. We'll have moles of mercury in the top and moles of mercury 2 oxide on the bottom. The last piece of this equation is to go from moles of mercury to grams of mercury. For that, we need to use the molar mass. Again, make sure you use the right one. This time, the number of grams is going in the top because we want grams at the end. And we want to cancel out the moles of mercury. So let's walk through this and make sure that our units are correct. The first step, we're going from grams of mercury to oxide to moles. So we're canceling out the grams, and we're left with moles. Great. Next, we're using that mole ratio between mercury and mercury 2 oxide to figure out how many moles of mercury we'll produce. That means we're getting rid of the moles of mercury 2 oxide, and we're left with moles of mercury. The final piece is taking the moles of mercury and converting to grams. We use the molar mass, put moles on the bottom, and we're left with grams of mercury on the top. After you do the unit analysis, then you can touch your calculator and put in all the numbers. Whenever you see a number in the denominator that is not 1, you need to do division. So remember to multiply and divide. When you do all of that, and you take sig figs into account, you should get 1.16 grams of mercury. Let's keep going. The next problem type that we're going to encounter is mass to volume. So you're taking a given mass and you're converting it to the volume of a reactant or product. So let's say that our product is a gas, and we're starting with grams of A. We're going to take those grams of A and convert them to moles. That's always the first step, taking whatever you have and getting to moles. Then you use a mole ratio to get from moles of A to moles of C. Now you have the number of moles of C. But we need a volume. So we need to use molar volume from chapter 8 to figure out how many liters of gas we have. So remember, in 1 mole of gas, there's 22.4 liters. That's how you get from mass to a volume. Now let's put a little bit of realness to it and do a problem. Let's say that we have aluminum metal and we're combining it with dilute hydrochloric acid at STP. Remember, molar volume has to be at STP, so you'll see that in the problem. And the question is, how many milliliters of hydrogen are produced from this reaction? We have to first identify the type of problem, because again, you're not going to have a title that tells you. The question is asking for the number of milliliters of hydrogen. Milliliters is a volume. So we know that's what we're trying to figure out. what we're given is a mass of aluminum metal. So that makes this a mass to volume question. Since we know it's a mass to volume question, we know that we're going to need the molar mass of aluminum to figure out the number of moles. For that, you just go to the periodic table. And just like before, I'll write out the plan in all the colors and then write the unit factors that are associated so you can follow along. Starting with the number of grams of aluminum. Oops. Not supposed to be doing that yet. We're going to go to moles of aluminum. Again, that's using the molar mass. Next, we have to figure out how many moles of hydrogen gas we make. We need a mole ratio for that. We'll go to the chemical equation, figure out how many moles of aluminum, how many moles of hydrogen gas, and write a fraction, and then we'll figure out which one of those fractions we need to use. This last piece, which is a little bit different than before, we're trying to figure out the volume. That means we have to use molar volume to convert moles of hydrogen gas to liters of hydrogen gas. For this question, we have to report our answer in milliliters. I'm going to leave this like this, and we'll do that conversion at the end to get to the final answer. But in general, this is how you go from mass to volume. Let's add the numbers in. Our starting mass is 0.165 grams of aluminum. We already have our molar mass, and that was straight from the periodic table. Again, write all your units when you're writing these unit factors out. It will only help you. Next comes our mole ratio. So let's write those up at the top. We're dealing with aluminum and hydrogen gas. Notice how I'm ignoring everything else in the equation, like it doesn't even exist. We need to have a mole ratio that only talks about aluminum and hydrogen gas. So you write the numbers that you see for those. I've got 2 moles of aluminum and 3 moles of hydrogen gas. You can also have the reciprocal. 3 moles of hydrogen gas over 2 moles of aluminum. The one that will get us where we need to go is this second one here, because it will cancel out the moles of aluminum and leave us with moles of hydrogen gas. The last part is molar volume. So remember, 1 mole of gas has a volume of 22.4 liters. Since we're trying to get to liters, we will put that in the top and moles of hydrogen gas in the bottom. Now this last part, which I'm putting in black, is how we convert from liters to milliliters. You won't have to do that for every single question. But since that's what the units are for the question in this case, that's what we should do. So that's a throwback to chapter 2. There are 1,000 milliliters in 1 liter. Now, we need to go back through and do our unit analysis. We're starting off by getting rid of grams, and we've got moles. And you can see that lines up with what we're trying to do in our plan. So if writing out the plan helps you so that you can make sure you're setting up your unit factors correctly, do it. The next part is to take those moles of aluminum and figure out moles of hydrogen gas using a mole ratio. And when we do our math, that's what we're left with, moles of hydrogen gas. The next part is molar volume. We cancel out the moles and we have liters. And then for this question only, we're getting rid of the liters and answering in milliliters. When you do all of that, you should get 205 milliliters of hydrogen gas. Don't forget your units, because leaving me with 205 doesn't tell me what you have. Likewise, if you're writing out all of these unit factors, please put units, because it helps me see what you're doing. Sometimes you'll have numbers that are very similar in different unit factors. You don't want me to be confused, because if I'm confused, you get fewer points. Okay? So be clear. It'll help you get to the right answer, and it'll help me give you as much credit as possible if you don't get to the right answer. Let's do a reverse of that problem. Instead of starting with the mass, we're going to start with the volume. How many grams of sodium chlorate are needed to produce 9.21 liters of oxygen gas at STP? First thing you have to do is identify. The question is asking how many grams. That's a mass. The given information, which is the number, is a volume. So we're going from the volume of a gas to the mass of a different reactant. We're still going to need a molar mass here. The molar mass of sodium chlorate. You should remember how to do molar masses. So I'm not going to go through the trouble of writing out how I got this. But if it is struggle bus, please let me know. So that's what we're starting with. Molar mass. And then we've got all of our starting information between the problem and the equation. So let's write out the plan. This time we're starting with liters of oxygen gas. That's our given. We're going to use molar volume to convert those liters to moles. So last time molar volume was purple. It's purple this time too. Then we need to get from moles of oxygen gas to moles of sodium chlorate. We'll use our mole ratio here. We have to figure that out from the chemical equation. The last piece is figuring out the number of grams of sodium chlorate. And that uses the molar mass, which we've already calculated. Let's add some numbers to this. Starting with our volume of 9.21 liters, we'll use molar volume to go from liters of oxygen gas to moles. Notice how this time the liters of gas are in the bottom of the unit factor. That's because we're trying to convert to moles. In the previous problem, we were trying to get to liters. Next, we need a mole ratio. We're only looking at the sodium chlorate and the oxygen gas. We're completely ignoring everything else in the equation. Let's write a fraction. Now let's write the reciprocal. We're trying to get to the number of moles of sodium chlorate. So we need to cancel out the moles of oxygen in the top by having moles of oxygen in the bottom. That means we're going to use this first unit factor. The last piece of our equation is going to take the moles of sodium chlorate and convert to grams. We put the grams in the top because we want to end up with grams at the end. And the 1 mole goes in the bottom. Always do your unit analysis, please, because it will help you make sure that you put your unit factors in the right orientation, that you didn't flip one. You always need a unit in the top and the bottom to cancel. So just like with liters, we have liters on top, liters on the bottom. They cancel and leave us with oxygen gas. And that's the first part of our equation. The second part, we're trying to get to moles of sodium chlorate. We have moles of oxygen gas on the top and the bottom, so we can cancel those, and we're left with moles of sodium chlorate. The final piece is the molar mass. We've got moles on the top and the bottom for sodium chlorate, and we're left with grams. When you do that math, you should get 29.2 grams of sodium chlorate. The last type of problem that you'll see is volume to volume. In my opinion, these are the easiest. I'll give you a little bit of background before we get to solving a problem. So Gay-Lussac, he worked with gases, and we're going to see his name pop up again in chapter 10. One of the things he discovered is that the volumes of gases under similar conditions, aka same temperature and pressure, combine in small whole number ratios. And this is what's called the law of combining volumes. So if we have this equation where we've got hydrogen gas and chlorine gas combining to make hydrogen chloride gas, if we have 10 milliliters of each reactant, we're going to produce 20 milliliters of product. So those volumes combined, and it's a small whole number ratio, 1 to 1 to 2, which is exactly what we have for our moles, right? 1 mole, 1 mole, 2 moles. We could also say 1 liter, 1 liter, 2 liters, if they're all at the same temperature and pressure. So we can use this equation. Again, we're still using the all gases. And we can use them like the mole ratios, only with volumes. So 1 volume of hydrogen gas, 1 volume of chlorine, gives you 2 volumes of your product. With volume to volume, you're given a volume and you're asked about a volume. And there's only one step. That's why this is the easiest. You can use the given volume and a mole ratio, which is the volume ratio, right, from the balanced equation, to figure out the unknown volume. If we're starting with liters of A, not LA, but liters of A, then we can use a mole-mole ratio, which is the volume ratio. And I'll label that as a volume ratio because we're using volumes. But it's from the mole ratio. They're related. And that gives you the number of liters of C. That's simple. I know. You're welcome. How many liters of oxygen react with 37.5 liters of sulfur dioxide in the production of sulfur trioxide gas? How many liters? That means our question mark, liters of oxygen gas. React with, and we're given another volume, 37.5 liters of sulfur dioxide. That's a volume to volume. We're just identifying the pieces of information as a mass or volume, and then seeing what type of problem we have. Now we know it's a volume to volume. It's a piece of cake. We're starting with 37.5 liters of sulfur dioxide. And since we've been using green for our mole ratio, that's what I'll use here. Only this time it's going to be liters for volume. Let's write out those two volume ratios. We care about the sodium or the sulfur dioxide and the oxygen gas. See, I'm still writing moles because I'm so used to moles. We've got 2 liters of sulfur dioxide gas for every 1 liter of oxygen gas. And then we can write the reciprocal. The one that we need has sulfur dioxide in the bottom, so we can cancel out those liters and be left with oxygen gas. Our units cancel out, and now you have to do the math. You should get 18.8 liters with sig figs. That's it. I know, you're probably waiting for the other shoe to drop. There's no other shoe. That's it for volume to volume. But there is still more. So maybe this does count as the other shoe. Now we've got to talk about limiting reactants. Before we talk about the chemistry, we're going to talk about food, because you know I use food analogies all the time. Why? Because everybody eats. Let's say you're making a grilled cheese sandwich. For just the most basic of basic grilled cheese sandwiches, you're going to need 2 pieces of bread, 2 pieces of cheese. That's going to make 1 sandwich. So we can write that like an equation. 2 cheese, 2 bread, 1 sandwich. Let's say that I have 10 slices of cheese, but I've only got 2 slices of bread. I can only make 1 sandwich still. I've got enough cheese to make 5 sandwiches, but I've only got enough bread to make 1 sandwich. And just melting cheese in a pan is not a sandwich. So the limiting ingredient here is the bread. Even though I have more cheese to make more sandwiches, I can only make 1 sandwich here. The cheese is in excess. Now in my house, it's usually the other way around. We don't have enough cheese, but we got all the bread in the world. We can use that same logic to talk about a limiting reactant. That limiting reactant is going to control how much product you can make at the end. It gets used up before all the other reactants. I'll show you what I mean. Let's say that we heat 2.5 moles of iron and 3 moles of sulfur. And we're trying to figure out how many moles of iron 2 sulfide are formed. And we want to identify the limiting reactant. I like to write in the amount that I have of each reactant or product so that it helps me. So just how I did there, that helps me to see what the question is. And since I've got 2 amounts, that tells me already that I've got some kind of a limiting reactant question. The first step is to figure out how much iron 2 sulfide we would make if we had 2.50 moles of iron and unlimited sulfur. We would do that the same way that we've been doing it. You take the number of moles of iron, you write a mole factor, or mole ratio, same thing. That will get us from the number of moles of iron to the number of moles of iron 2 sulfide. So if we just had that 2.5 moles of iron and unlimited sulfur, we'd make 2.50 moles of iron 2 sulfide. Now we have to do the same thing for the sulfur. If we had 3 moles of sulfur and unlimited iron, how much iron 2 sulfide would we make? Starting with our moles of sulfur, we write a mole factor. It's going to look pretty similar to the one that we just wrote. So if we had 3 moles of sulfur and all the iron in the world, we could make 3 moles of iron 2 sulfide. Now let's come back to reality, because what we're really doing is combining 2.5 moles of iron and 3 moles of sulfur. So whichever one makes the least amount of product is the limiting reactant, and that tells us how much product we're actually going to make. 2.5 moles of iron 2 sulfide is less than 3 moles. So we're going to make 2.50 moles of iron 2 sulfide. Remember, again, that's the least amount of product formed. The limiting reactant is the reactant that we started with. So this one was from the iron. That means iron is the limiting reactant. We can take this concept and combine it with the different problem types that we were doing, the mass to mass, mass to volume, and volume to volume. This says in words kind of what you'll need to do. I always think that it's better to just do a sample problem. But if you're a word type of person, you want to put this in your notebook, totally cool. Go for it. Let's try a problem. How much molten iron is formed from the reaction of 25 grams of iron 2 oxide and 25 grams of aluminum? Since we're seeing 2 reactants here, we're given 2 masses. That means that it's a limiting reactant problem. So we need to know that. We also need to know what type of problem it is in terms of the calculation we need to do to figure out how much product we make. We're given masses and asked how much molten iron is formed. That suggests that we need to figure out another mass. So this is a mass-to-mass problem. What this means for our solving the problem is we need to do 2 individual mass-to-mass problems. One where we start with 25 grams of iron 2 oxide and figure out how much iron we make. And another where we start with 25 grams of aluminum and see how much molten iron we make. From there, we'll figure out which one makes the least amount of product, and that will tell us how much molten iron is formed when we combine these two reactants. I'll still write out everything in the kind of color-codedness, but I won't write out the plan. So for our first problem, we've got grams of iron 2 oxide, and we're trying to figure out how many grams of iron. We're going to need molar masses here. The molar mass of iron 2 oxide, you take the molar mass for iron and oxygen and you add those together. For iron, you just look at the periodic table. Now that we've got those pieces, we can get started putting our equation together. The starting information that we're given is 25 grams of iron 2 oxide. Since this is a mass-to-mass problem, we have to convert that first mass to moles. That always means molar mass. We need the molar mass of iron 2 oxide in this case, and the number of grams goes in the bottom. Please be careful when you're putting in your molar masses for a mass-to-mass problem. You have two of them to choose from, so make sure you pair them up properly. Next is our mole ratio. This is going to be directly from the problem. And I'm just going to write the correct one directly. We're dealing with iron 2 oxide and iron, so I underlined those. We want the iron to come out on top, and we cancel out the iron 2 oxide. The final piece is finding out the number of grams of iron that we're going to make at the end. The grams go on top from your molar mass of iron, and moles go on the bottom. We make sure everything cancels. And if it does, we do the math. But that's only one part. That tells us how much iron we would make if we had 25 grams of iron 2 oxide. The problem says that we also have 25 grams of aluminum. So we need to figure that out too before we can establish which one is the limiting reactant and how much iron we actually make. Our second problem is still mass to mass. We've got grams of aluminum, and we're trying to figure out how many grams of iron. We still need molar masses here. The molar mass for aluminum, you get directly from the periodic table, and I will simply rewrite the molar mass of iron here. Now we set up our equation just like we did before, only instead of iron 2 oxide, it's aluminum. Molar mass is first. This time it's the molar mass of aluminum. Next comes the mole ratio. I'll do a dotted circle here. We care about aluminum and iron. Just like in the first part of the question where we were going from iron 2 oxide to iron, we want the iron in the top. And that came directly from the chemical equation. We want to write the moles of iron, or excuse me, the moles of aluminum in the bottom. So that's 2 moles of aluminum. This last piece where we're converting moles of iron to grams of iron is going to be exactly the same. Go through and do your unit analysis, making sure that you cancel one on the top and the bottom. If you've only got one on the top or one on the bottom, you can't cancel it out. Now that we've figured out how much iron we can make in both of these scenarios, we need to look at them and go back to reality because we're combining these two. So we're either going to make 19.4 grams of iron or 77.6 grams of iron. You're going to choose the one that makes the least amount of product. And in my book, 19.4 is much less than 77.6. Somebody gave you $20 when they promised you 80, there'd be a difference, right? So 19.4 grams, definitely smaller. That's how much of the molten iron we're going to produce. If you write it out as just a quick little sentence, make 19.4 grams of iron, something like that, versus circling it within your work and just leaving it at that, it will make my life a lot easier because I'll see exactly what your answer is. If I have to go hunting for your answer, I may not find it. And that's frustrating for both of us. So make it easier on me. Show me. Tell me. Make it plain as day what your answer is. And we're not asked which one is the limiting reactant, but if we were, we would say, okay, I made 19.4 grams of iron, and what did I start with? I started with iron 2 oxide. So that is the limiting reactant, which I abbreviate LR. We can do the same thing with gases. So this is just another example. How many liters of nitrogen dioxide gas can be produced from 5 liters of nitrogen monoxide gas and 5 liters of oxygen gas? So this was the same reaction that we started with at the very beginning when we were learning how to interpret chemical equations. Remember, you have to identify not only that it's limiting reactant, because you've got 2 pieces of given information here, and you're asked about one product, but you have to say, okay, is it mass to mass, volume to volume, mass to volume? What are we dealing with? And since we've got 2 volumes, it's volume to volume. So just like before, we had to do 2 problems. We're going to do the same thing here. The first one is with the nitrogen monoxide. The second one we'll do with the oxygen gas. Let's take those 5 liters of nitrogen monoxide gas and figure out how much nitrogen dioxide gas we'd make. All we need to do is figure out the volume ratio, which is the same as the mole ratio, only instead of moles, it's liters. We look at the equation and we ground ourselves. Okay, we're using these 2 and we don't care about anything else. Now let's write one. We need to cancel out the nitrogen monoxide. So the moles of that from the equation should go on the bottom. That leaves the moles of the product to go on top. And I wrote moles, even though I was thinking liters. I've got moles on the brain. So that's the first part. We know how much we'd make if we had unlimited oxygen gas and 5 liters of nitrogen monoxide. Now we need to do the same thing for the oxygen gas. We're looking at oxygen and nitrogen dioxide. We still want those moles or liters of nitrogen dioxide in the top, just like before, but in the bottom, we're going to put oxygen gas. Now that we know how much we would make if we had one reactant and excess of the other, we need to come back to reality because we're combining these 2. We're either going to make 5 liters or 10 liters. You choose the one that makes the least product. 5 liters is definitely less, so we'll make 5 liters of nitrogen dioxide. If we had to say which reactant was limiting, it would be the nitrogen monoxide. Again, that's not part of this question, but I'm throwing it in there just so that you can practice and you can identify which reactant is the limiting reactant. The final concept that we're going over for Chapter 9 is percent yield. When you actually do an experiment, the amount of product that you make is called the actual yield. And the actual yield is rarely, if ever, what you calculate. You might lose some of the product, maybe it sticks to the weigh boat. Maybe one of the reactions that you're doing is not as efficient, so all of the reactant doesn't get converted to product. Needless to say, you're usually not going to make as much as you calculate that you should. The amount that you calculate, that's the problems that we've been doing. And that's called the theoretical yield. So the mass to mass, mass to volume, and volume to volume, those are all ways of calculating the theoretical yield of a reaction. The percent yield is a ratio of the actual yield to the theoretical yield, and then you multiply by 100%. So that tells you how good you did. Let's do a quick example. Suppose a student performs a reaction and obtains 0.875 grams of copper 2 carbonate, and the theoretical yield is 0.988 grams. What is the percent yield? The trick here is identifying which one is the actual yield and which one is the theoretical yield. Performs a reaction and obtains 8.875 grams. That tells you it's the actual. It's what you got. It could also say something about an experiment yielded this amount. That would be the actual yield. The theoretical yield is spelled out. The theoretical yield is 0.988 grams. This is the equation. And you just need to make sure to put the right thing in the right place. The actual yield goes on top. The theoretical yield goes in bottom. You divide those two numbers, multiply by 100%, and you should get 88.6% yield. Word to the wise. Percent yield questions are not always going to be this straightforward. I could give you a mass to mass question, or a mass to volume, or a volume to volume, and tell you what the actual yield is. You'll never have to figure out the actual yield because you can't. You're not going to do the experiment. But I could tell you, for example, that you have, this many grams of one product, or one reactant rather. How many grams of the product do you make? And that would be a mass to mass. And then the next part could be the actual yield was blah, blah, blah grams. What is the percent yield? So we'll do some problems like that in class to combine the stoichiometry problems with the percent yield. So make sure you come to class. And if you're watching this after class, I hope you came to class, because sometimes those can be tricky. That's it for Chapter 9. It seems kind of short, but practice, practice, practice. That's why we're going to take 2 weeks to go over it. You have your Chapter 9 Mastering Chemistry due Sunday, November 15th. And then Exam 4 is coming up this week. So that covers Chapters 7 and 8. And it will be available Wednesday, October 28th. Got to submit it by Friday, October 30th. So right before Halloween. As always, you come to office hours, 2 to 4 p.m. You can send me a course message through Blackboard. If you need to set up an appointment outside of that, or if you need a little help, you can send me a question and I can shoot you back a response. Either way, if you need something, that's how you can get to me. Until then,